Right now, your phone knows exactly where you are, down to a few meters. But how? You're holding a device that can pinpoint your location anywhere on Earth using satellites 20,000 kilometers above your head. This isn't magic. It's one of humanity's most ingenious engineering achievements. I am Nikhil, and as an aerospace engineer turned educator, I've always been fascinated by how GPS works. Today, we're going to uncover the surprising science behind how your phone knows your exact location. We'll explore why GPS needs atomic clocks, more precise than anything on Earth, how your device does math with light speed calculations, and why timing errors of just 1 microsecond would put you 300 meters away from where you actually are. GPS isn't just one satellite, it's a constellation of at least 24 satellites, currently 31, arranged in 6 orbital planes around Earth. Each satellite orbits at an altitude of 20,200 kilometers. That's about halfway to geostationary orbit. They complete 2 orbits every day, traveling at 14,000 kilometers per hour. This careful arrangement ensures that from anywhere on Earth's surface, you can always see at least 4 GPS satellites. That too, above 15 degrees on the horizon. Why 4? We'll get to that shortly. It's the key to the whole system. Each GPS satellite is essentially a flying atomic clock with a radio transmitter. They are solar powered, about the size of a small car, and cost around $50 million each. But here's what makes them special. They carry multiple atomic clocks that are accurate to 14 nanoseconds. To put that in perspective, if you had a clock this accurate when Buddha was born, it would be off by less than 2 seconds today. So, how does your GPS receiver figure out where you are? It uses a mathematical technique called trilateration, not triangulation, but trilateration. Now, the difference is crucial. Triangulation measures angles, but GPS measures distances. Here's how it works. Each satellite continuously broadcasts 2 pieces of information: its exact location in space and the precise time the signal was sent. Your GPS receiver records when it receives each signal. Since radio waves travel at the speed of light, your receiver can calculate its distance from each satellite using this simple formula. Distance equals speed into the time difference. Now, with one satellite, you know you are somewhere on a sphere around that satellite. With 2 satellites, you are somewhere on the circle where those 2 spheres intersect. With 3 satellites, there are only 2 possible points where all 3 spheres meet, and one of them is usually in space. So your location is the other point where the 3 spheres are intersecting. But there's a problem. Your phone doesn't have an atomic clock. Your phone's quartz clock is accurate to maybe 1 part in 10,000, which would create errors of several kilometers. This is why GPS needs a 4th satellite. That 4th measurement allows your receiver to solve for 4 unknowns: your X, Y, and Z coordinates, plus the error in your clock. Let's talk about why timing is so critical. Light travels 300 million meters per second. This means that a timing error of just 1 microsecond, 1 millionth of a second, translates to a 300 meter error in your position. A nanosecond error, that's still a 30 centimeters mistake. This is why GPS satellites carry atomic clocks. Devices that lose less than 1 second every 3 lakh years. But here's where it gets really interesting. Those satellite clocks don't just need to be accurate, they need to account for Einstein's theory of relativity. Because the satellites are moving fast and experiencing less gravity than we do on Earth's surface, time literally runs differently for them. The satellite's speed makes their clocks run 7 microseconds per day slower than Earth clocks. But the weaker gravity makes them run 45 microseconds per day faster. The net effect? Satellite clocks gain 38 microseconds per day. Without correcting for this, GPS would accumulate 10 kilometers of error every single day. GPS satellites broadcast on multiple frequencies. The main civilian signal transmits at 1575.42 MHz. Each satellite sends a unique pseudo-random code, essentially a complex barcode, along with navigation data that includes the satellite's position, time, and health status. Your receiver has to find and lock onto these incredibly weak signals. By the time a GPS signal reaches Earth, after traveling 20,000 kilometers, it's weaker than the signal from a 25-watt light bulb, viewed from 25,000 kilometers away. Your phone is essentially detecting whispers from space. Several factors can introduce errors into GPS positioning. The atmosphere is the biggest culprit. As GPS signals pass through the ionosphere and troposphere, they slow down and bend slightly, creating delays that translate to positional errors of 1 to 5 meters. Multipath errors occur when signals bounce off buildings, mountains, and even the ground before reaching your receiver. This is why GPS often struggles in urban canyons or under tree cover. The reflected signals travel further, arriving later and confusing your receiver about the actual distance to the satellite. So, how accurate is GPS in practice? Your smartphone typically gets you within 3 to 13 meters of your true position. That's pretty good, but it can be much better. Differential GPS systems like WAAS can improve accuracy to 1 to 3 meters. Survey-grade equipment using real-time kinematic positioning can achieve centimeter-level accuracy. But GPS isn't just about knowing where you are. Modern life depends on GPS timing for far more than navigation. Every time you make a credit card purchase, GPS timestamps ensure the transaction happens in the right order. Cell phone towers use GPS to synchronize their networks. The electrical power grid relies on GPS timings to keep power floating efficiently across thousands of miles of transmission lines. Even internet data packets are often time-stamped with GPS time. This dependency has created new vulnerabilities. GPS signals are so weak that they can be easily jammed or spoofed, which is why backup timing systems are becoming critical for national infrastructure. So the next time you ask your phone for directions, remember, you're using a system that requires atomic clocks in space, accounts for Einstein's relativity, processes signals weaker than starlight, and performs complex mathematics 30 times per second. GPS represents one of humanity's greatest technological achievements, a system so sophisticated that it makes the impossible seem routine. From military origins to civilian revolution, GPS has transformed how we navigate, communicate, and organize modern society. And with new satellites launching and improved algorithms, it's only getting better. What questions do you have about GPS? Drop them in the comments below. And if you enjoyed this deep dive into the science behind everyday technology, subscribe for more engineering explanations that reveal the hidden complexity of our modern world.